Alright, we're now to the final part, part 3, logic. So, the two things I'm going to talk about, um, if and only if and implication, and quantifying things. So, what does this mean? A implies B. So when we read this, we say A implies B. Like that's the terminology that we use. That's what we call this when we read it. But what's really happening is that A is a predicate. This is something with a truth value. It's either true or false. B is another predicate. It's another thing which is either true or false. And when you write this symbol in between it, you create this whole thing is now a single predicate. This is a way of combining two predicates together, and now you assign it a different sort of true or false value depending on whether these are true or false, according to the truth table of implication. Same thing with if and only if, right? It's a way of combining predicates together to make a new predicate. And these are just symbols of classical logic, and it's all sort of staying within that system of logic. Okay, so what this is not equal to is, so for example, if we have vector A implies B, right? This is not saying that A is true, therefore B is true. This whole thing is a single object which has a truth value. You can't think of it as different parts of, or different objects related by this truth thing where if A is true, then B is true. That's a result of something called the deduction theorem, which you can learn about in Math 315, I guess, but not yet. So I'll give an example. Someone might say something like, dot, 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 therefore P is even, implies that P equals 2Q for some Q in Z. Alright, someone might something like this. So they might say, alright, P is even, which implies that P equals 2Q for some Q in Z. So by definition, a number is even if you can write it in the form 2Q for some Q in Z. Sure. But in a proof, if you're trying to prove something, you start with your initial step, and then you have your logical reasoning, deduction stuff, and then you get to your last step, right? So I'm going to introduce a symbol, the turnstile. Turnstile, I think that's what it's called, because this is what you guys are actually talking about if you write this. Right? So if we just look at this sentence, we say therefore P is even, which implies this, but this doesn't make sense because this isn't a predicate. Well, I guess this is a predicate, so half of it's okay, but you can't just randomly put an implication symbol here because you can only use this if you're joining two predicates together to make a new predicate. So what you guys are really talking about is if you have something which is true, right? You have something which is officially true, right? And then from something true, you can say, all right, now I can deduce that this other thing is true, right? And then that, if you can deduce something, in logic you use this symbol here, and it says, all right, I can deduce that this other thing, right? So this here is like a meta-logical statement, right? So you're going outside of the logic system, and you're saying that within the logic system, if this is true, then this is also true. And this is logical deduction. This is deduction happening outside of the system of logic, right? But if you have the implication symbol, that's all staying within the system of logic. So it doesn't make sense to put an implication symbol here, unless what you're really talking about is concatenating two different predicates together, which is not what you're doing, right? You're trying to have steps of reasoning to reach a proof. So what I'm really saying is don't use that symbol because it's not being used correctly if you're using a proof like this. Just say, this is true. Just write therefore, right? That's fine. It's more correct. And if you don't want to say therefore like 10 times in a row, you can alternate it. So what I do is I write therefore, no, I go hence, And then next time it has to come up at right hands again. Then I write therefore. And then I write thus. And then repeat. And I don't know, it reads kind of nicely. But it's a lot better than writing the implication symbol because that's technically wrong. Alright. Okay. We're up to the last part now. Quantifying things. Okay, I'll use an example from the assignment again. So let's say we have a statement. N is odd implies. No, I'll use words. If N is odd, then N equals 4q minus 1. Right, if n is odd, then n equals 4q minus 1 or n equals 4q plus 1 for some q in the integers. Okay, so let's say you're told to negate this. What's the negation of this? It's n is odd and n equals, n is odd and n is not equal to 4q plus 1 and n is not equal to 4q minus 1 for any q in the integers, right? But almost everyone wrote this. For all n in the integers, n is odd, and n is not equal to 4q plus 1, dot, 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 right? Almost everyone put this here. But if you look at the original statement, it doesn't say anything about for all n in the integers. It's just n, right? It just says n, that's it. It's not quantified. So if you negate it, there's no way that a quantifier is going to appear out of nowhere. And you might say, hey, but isn't there an implicit quantifier in here? Because if this statement here, if this is true, if n is odd, then this, surely this is true only if it's true for all n, right? It sounds like it should be implicitly universally quantified. But that's not true, right? So imagine a statement like this. Pi greater than 3. If you just saw that, you'd say that it's true because we automatically think that pi is equal to 3.1415926, whatever. But what if it said for all pi in z? Right? Pi is just a symbol, right? It can take different values. It can take the pi that we're used to, in which case this is true. But if it's this, then it's not true, right? This is definitely not true, because choose pi equal to -1. It's not true anymore. But now if it had an existential quantifier, again, this is definitely, now it's definitely true, right? There exists pi in z. Yeah, there is, because you can choose pi equal to 5. You might say that this looks a bit artificial, and it's avoiding the implication. So let's see. So the reason the universal quantifier shouldn't appear is because there could be a line above here that says n is equal to 10, right? Then this is true because it's vectorally true because n isn't odd, so the implication is true. On the other hand, if n equals 9, maybe it is false, maybe it's false, I don't know. And if you have a completely different statement, then by changing n, by setting n equal to different things, the truth of the implication can change, right? So there's nothing here that tells you that it's for all n in the integers. So be careful about whether things are quantified or not. In general, I guess just thinking about what the statement's really saying, and I was going to say in general, people tend to quantify too much, but that's probably not true because there are always cases where people don't quantify enough, so just try and figure it out, I guess. Alright, thanks for listening. Hopefully it was useful. like graduate text and memes on Facebook, and like mathematical mathematics memes, and go to the Red Bull page for graduate text and memes and buy some math merch that I designed. Alright, cool. Thanks, guys.